All right, so this is a for real problem. This happened to me when I was in graduate school. Somebody did it when I went to lunch, and I was the only chemist in a room full of biologists, and they couldn't remember how to make the materials. And as it turned out, nobody could figure out how to do these calculations, and I don't want that to happen to you. Don't become a graduate student who can't remember how to do molarity calculations. It's just embarrassing. They had to buy me lunch. Okay. So, by the way, when I was in grad school, I got a lot of favors by doing these kind of calculations for people. So I want you to be able to get the same advantage should you choose that path. All right, so here we have a molarity, and again, I'm going to translate that right away. This is a mental exercise that I have, that you have to develop. And we also know there's 500 milliliters. So we can multiply these, but they're not going to cancel. So I'll also have to do a conversion to get rid of milliliter, just like we did before. This will get us moles. And then, of course, you can't weigh out moles. So we need to also multiply by the molar mass so we can cancel the moles. So molar mass of Na3PO4 is going to be 3 sodiums right? So sodium is 22.989, so I round to the second decimal place, so 2299. These are small, these are for you. And then P, of course, is right here, so 30.97. And oxygen rounds to 16.00. So that's where I'm getting the numbers from. I put my parentheses in a dumb place. There we go. I already forgot what phosphorus was. Let's go check. Oh yeah, 30.97. And 4 oxygens. As it turns out, phosphate buffer, which is what this was, is a very common ingredient in biological systems. Phosphate is often the limiting reagent in biological growth, especially plant growth. All right, so our total here is 163.94 grams per mole. So I just wanted to demonstrate to you the importance of actually calculating your molecular weights on your own. I Googled sodium phosphate molecular weight, which is what most of you would probably have Googled. And we get the wrong value because it turns out there are many different salts made with phosphate in it. And this particular one only has 1 sodium. Ours is trisodium phosphate. And maybe if you Google that, you get a better answer. But it's just really not worth the stress of never knowing if you're right. So just calculate it on your own. Okay, so that's my tip for the day. All right, so 163.94 is going to go up here. And once we get all this math done, we'll know exactly how much sodium phosphate to weigh out. All right, so it's going to be 1 times 500, which is 500, divided by 1,000, which is 0.5. And then multiply that by 163.94. And so basically, we have technically 1 sig fig, but you're going to use something more precise than 1 significant digit to measure that. So we're going to go ahead and keep at least 2. 81.97 is what our calculator says. We're going to round that to 82 grams. And so that's what you'd weigh out, and then you would put it into like a volumetric flask, let's say, and you would dilute it up to 500 milliliters. We have a lot more precision than this because your scale is going to have at least 2 decimals. And 500 mils in a volumetric flask would be 500.00, so that's 5 sig figs, right? But then you can replace it before I do that. Okay. So going back to the idea of electrolyte solutions, which are those that break apart in water and form ions. So our categories were ionic substances that are soluble, acids, bases. Hopefully you're recognizing those things by now. When ionic things are put into water and they ionize, we don't always get the same concentration of each ion, right? So when we think about calcium nitrate, when we dissolve that, you're going to get calcium ions, and you're going to get 2 nitrate ions for every calcium ion, like that. So if we start with 1 molar of the parent compound, 1 molar of the solid, you're going to get, use mole ratios here, right? So there's also 1 molar of calcium ion, but there's not 1 molar nitrate, right? Because CaNO3, 2, if we use molar ratio, you're going to have 2 nitrates for every 1 parent compound, which means 2 molar, okay? So whether you think about this as a molarity or as moles, it's kind of the same process here. You want to be careful about reading the question to understand whether you're using an ion concentration or whether you're using the parent compound, right? It makes a difference.